Hi guys, in this video as promised, I'm going to show you how to do one-way ANOVA manually in Excel. If you are not interested in doing it manually, or if you want to first learn how to use the analysis tool pack, which automatically generates all the stuff we're going to do here, then make sure you watch that video, which I'm linking right here in this video. Okay, but if you want to learn how those numbers are calculated, that analysis does for you, this is the video to watch. Okay, so here we go. We got a one-way ANOVA, so we have 3 groups in this example to keep it simple but also illustrative of a typical one-way ANOVA example. Okay, we have group A, B, and C. Okay, and in each group we have 10 observations. Okay, let me just number that. Okay, so first I get the sums of each of these groups, then I get the averages of each one of these groups, the means, using of course the sum function, then using the average function, then I get the standard deviation, then I get the variance. Okay, and these numbers will come in useful for later computations. So that's easy enough. Okay, so we use a sum, average, standard deviation, and variance functions. So the first thing we need to compute, and down here I've actually included the analysis tool pack's output so that we can get everything that the analysis tool pack automatically gives us. We're going to learn how to compute manually here. Okay, so first things first, the count. There's 10 in each, right? So for that we can just look at our number of observations here, right? Each one of these groups has 10, a count of 10, right? Here are the sums we computed, here are the averages we computed, and here are the variances we computed, and they all match up. Okay, now we move on to computing the more interesting things, the sum of squares. First, let's do the sum of squares between. Okay, to do the sum of squares between, I've actually done that in this area over here. Okay, so the grand mean is necessary here. So the way you can do the grand mean, it's just the average of the entire 3 groups. Okay, so just use the average function and highlight all 3 groups. Okay, so the grand mean here is 50.77 roughly. Okay, and oftentimes this is symbolized by x bar dot dot with 2 dots, right? Okay, so just follow along with the formulas you have in your textbook and everything will make sense. Okay, the next thing we need to compute is the sum of squares between, now that we have the grand mean. And to do that, we use the formula you have. We get the count group by group. Okay, so this is for group A, this is for group B, and this is for group C. So for group A, we get the count of observations in group A, which is over here. And then we multiply that, as you see over here, the multiplication sign, by the group A's mean minus the grand mean of all 3 groups squared. Okay, as you can see, squared. Okay, so again, the count of the group times the group mean minus the grand mean squared. Okay, and we get 8.711, and we do that for group B. Okay, just using group B numbers. Okay, as you can see, everything just shifted to group B, but the grand mean stays the same. Okay, and then again for group C, everything's shifted to group C. Once we have all 3 of these components, we can get the sum of squares between. Okay, and that is done by simply summing these 3 components. The 3 sum of squares add up to the sum of squares between. And if we can take a pause right here, this 454 in purple matches this 454, which Excel automatically generated for us exactly. Okay, so we're able to compute this figure by ourselves manually. and we know how it's done, most importantly. Now let's get the degrees of freedom for the sum of squares between. The way we do that is just the number of groups, which is represented by the symbol k, minus 1. So here we have 3 groups, A, B, and C. So 3 minus 1 is 2. And that matches with this degrees of freedom. Okay? And then finally, for between groups, source of variance, we want the mean square between. Okay? And to do that, you simply divide the sum of squares by the degrees of freedom. So if I go into this formula, it's simply I7, which is this, divided by I8, which is the degrees of freedom. So 454 divided by 2 gives us 227.43, which is exactly what we have over here. Okay? So everything's matching up so far with what Excel automatically outputs with the analysis toolpath. Okay? Next, we're done with between groups. Okay? We're done with this row. We can move on to within groups and find out how to compute these figures. This one's a little bit more involved, but with Excel it's not that difficult because it automatically can drag formulas around. You don't need to do a lot of work by hand. The way you do this is you take in each group, you basically take each figure, each observation, subtract it from its respective mean, and then square that. Okay? And then do the same thing with the next observation. Take the next observation, subtract the mean from it, and then square it. All the way on down to the last observation in that group, subtracted by its mean, and squared. And then you're done with group 1. Group A, I should say. Okay? Then you move on and you do the same thing in group B. I'll just show you real briefly. You take the first observation in group B, you subtract group B's mean, and then square it. And so on and so forth, all the way on down to the last observation minus the mean, and then square it. And then you do the same thing for group C. Okay? And once you've done this for all 3 groups, for every single observation in each group, you'll get a table that has the same dimensions as our original table. It's got 10 rows, right? 1 all the way on down to 10, and it's got 3 columns for our 3 groups. And then we can easily compute the sum of squares within by summing all the numbers in this table. So we can do a simple sum function equals sum, and then highlight the entire table here, hit enter, and we get 13,654.5, and we see that that matches up exactly with what Excel's analysis toolpath gets us. So the sum of squares within groups is 13,654.5. Next, we need to get the degrees of freedom for that, for the sum of squares within. And the degrees of freedom for that is the number of groups times the number of observations in each group minus 1. And our number of groups is 3. The number of observation in each group is 10. And minus 1 would mean that this is 3 times 9. And that's why we get 27. That's how we get 27, and that 27 matches up exactly with what the analysis toolpath gives us. Okay? And finally, of course, we've learned to get the mean squared of anything, you take the sum of squared divided by its respective degrees of freedom. So the first number here divided by the degrees of freedom here gives us the mean square within. Okay? If I go in here, you can see that for yourselves. And we get 505.72. That matches up exactly with what the analysis toolpath gives us. Okay? So the hard part's done now. Now the fruits of our labor will start to show. To get the F statistic here, we just simply divide the mean square between by the mean square within. Okay? You might use different symbols for mean square between and mean square within. Some people call mean square between mean square among. I've seen different things, notations like that. Just make sure you're on the same page as me. There's not many different ways of writing this, but there are a couple, so just don't get too confused. Okay? So the mean square between, which we got over here, we computed ourselves, and the mean square within, which we got over here, divide these two numbers and we get this figure over here. Okay? So, sorry, wrong arrow. Let me draw those arrows again. This figure, the mean square, and this figure. Okay? Let me write that down again. The mean square between, that's coming from up here, and mean square within, that's coming from here. So it's 227.43 divided by 505. And that's how we get over here 0.44972. Okay? And then this in turn matches up exactly with what the analysis tool pack gives us automatically. Okay? So we got our F statistic, 0.44972. Now we can learn how to get this p-value. Well, to get the p-value, we need to use a special function built into Excel called the fdist function. Actually, there's a newer version of this function called the f.dist, I believe, .rt in the newer versions of Excel. Okay, so just look into that. They'll both give you the same figure. That newer one is supposed to be slightly more accurate and updated, but this gives us the right number, so we're just going to stick with this. So the function is up here, as you can see in the formula bar, equals fdist, open parentheses. The first argument is k21, which is our F statistic. Okay, that's the first argument in this function. Then you hit comma. The second argument is the degrees of freedom of the numerator. And the degrees of freedom of the numerator is coming from the sum of squares between degrees of freedom, which is I8. Okay? And then the final item is the degrees of freedom of the denominator. And that's coming from the within sum of squares within degrees of freedom. Okay, so I'm going to swing this around this way so as to not cross over anything. So there's three arguments. There's the F statistic we computed, the numerator degrees of freedom, and the denominator degrees of freedom. Okay, and then you close the parentheses, hit enter, and you'll get this p-value. And the p-value is really our ultimate goal. Okay, and you can see this p-value matches up exactly with what the analysis tool pack generates for us, 0.6425. And that's obviously not significant, right? Because it's much greater than alpha. Even if alpha was 0.05, 0.10, 0.1, anything, this is much greater than any alpha you'd ever use in a hypothesis test. So we obviously would not reject the null hypothesis here, right? And just to recall, the null hypothesis is that all three of these means are equivalent. So mu A equals, mu B equals mu C, right? We cannot reject that. So just to recall some of the theory of this subject, okay? Finally, we want to learn how to calculate this F critical, which is another way of getting the same result. Okay, so the way we compute this F critical is with another function built into Excel called the finv function. Okay, so in order to use this function, we type equals finv, open parentheses, then you put in your alpha. Okay, so here we put in our alpha. Our alpha for this test was 0.05. Okay, so we put in 0.05, comma, numerator degrees of freedom, which was exactly like our previous function, f dist, and then denominator degrees of freedom. Okay, so we had 2 numerator degrees of freedom and 27 degrees of freedom in the denominator, and we put our alpha in, and this will give us the f critical value, which is 3.35, and which it matches up exactly with the analysis toolpack's output. Okay, now what does that mean? Just a brief reminder, the F distribution looks something like this. It's right skewed, has a long tail on the right side. This F critical value, say it's right around here. This is the value such that any value more than this value will result in a rejection of the null hypothesis. So you can call this the rejection region. Okay? Anything greater than this value is a rejection region. And what does that mean for us? Well, we compare our F statistic, which we computed manually, with this F critical. This is our F statistic. It's also the same over here. Okay? And our F statistic will fall somewhere well to the left of this 3.35, right? 0.449 would fall well to the left outside of the rejection region, and thus we do not reject. So the p-value and the F critical are two ways of getting to the same conclusion, which in our case is we do not reject HO, the null hypothesis. Okay? And finally, to just be thorough, down here they give us this total sum of squares and the total degrees of freedom. To get the total sum of squares, we know it's just sum of squares between plus sum of squares within, and that's what I typed over here. It's the sum of those two, and that gives us exactly this figure over here. And the degrees of freedom is also the same. We're adding up the degrees of freedom of between with the degrees of freedom of within, and 2 plus 27 is obviously 29, and that matches up here. And remember that in analysis of variance, we're basically taking the total sum of squares, which is this number down here, and we're dividing it up into a sum of squares between and a sum of squares within. Okay? That's the ideology behind this methodology. Okay? So I hope this video was helpful. If you want to learn how to install the add-ins to do this automatically, now that you know how to do it manually, make sure you watch my video on Excel add-ins. If you also want to learn how to do the process of using the analysis toolpack, make sure you watch the video on ANOVA with analysis toolpack. Those are both on my channel. Be sure to subscribe to my channel. Again, support my subscribers. That keeps these video tutorials free. Make sure to check out my other Excel, Access, PowerPoint, Math, Statistics, and R tutorial videos. Till next time, have a great day.